Section 4.6 is on counting. And to begin with counting, we start with the multiplication counting rule. This finds the total number of possibilities from a sequence of events. And for a sequence of events in which the first outcome occurs n sub 1 ways, second event occurs n sub 2 ways, third event occurs n sub 3 ways, and so on from that, the total number of possibilities, we can just multiply all of them together. N sub 1 times n sub 2 times n sub 3 times whatever number of events that we have and the ways in which they could occur. So for example, in a linear triplet of 3 DNA nucleotides, each of the nucleotides can be any one of these 4 bases, with repetition allowed. A for adenine, C for cytosine, G for guanine, and T for thymine. 2 different examples of triplets are CTA and TTG. What is the total number of different possible triplets? Given that the 4 nucleotides are equally likely, what is the probability of getting the triplet of AAA? So, since we have a triplet, we have 3 potential options, 3 potential locations, I should say. And each of those locations can be any of these 4. So there's 4 for the first, 4 for the second, 4 for the third. So 4 times 4 times 4. That's the same thing as 4 to the third power, and that's 64. And to get the choice of AAA, that happens once out of that 64 or 4 thirds, or 4 to the third power. So 1 divided by 64, this gives us about 0.0156 as the probability. Next is this factorial rule, and this finds the total number of ways that n different items can be rearranged with different arrangements of the same items counted separately. And the factorial symbol, which is just an exclamation point, denotes the product of decreasing positive whole numbers, I should say. For example, 4 factorial is 4 times 3 times 2 times 1, and that's 24. The special case is 0 factorial, which is 1, and 1 factorial would also be 1. The number of different arrangements, order matters, of n different items when all n of them are selected is that n factorial. So for example, Quest Diagnostics collects blood specimens from different laboratories. A driver is dispatched to make collections at 5 different locations. How many different routes are possible? Well, that's 5 factorial, and that's 5 times 4 times 3 times 2 times 1. Toss that into a calculator, you get an answer of 120 possible routes. Possible routes. A permutation is an arrangement in which different sequences of the same items are counted separately. Order matters, meaning that A, B, and BA are 2 different permutations, since the order of A and B would be 2 distinct different options. A mnemonic that might help with this regard is that permutations position. So permutations have a specific position. A combination is an arrangement in which different sequences of the same items are counted as being the same. Order does not matter, meaning that A, B, and BA are the same. They're the same arrangement, just occurring in a different order. But since we don't care about order for this, they're both the same. A mnemonic for this is that combinations committee, meaning that one of the typical and mostly seen options when it comes to combinations are with regards to committee structures, meaning that just because you need to choose 5 people for a committee, if one person's their first, second, third, fourth, or fifth chosen, that person's still in there, and likewise the other 5 people are the same way. So if you choose a set of 5 people, no matter what order they're in, it's the same committee, the same combination of people. Now, when it comes to permutations, we have this permutation rule in which all items are different. There are n different items are available for selection. We must select all of them without replacement. And the sequence of the items does indeed matter. So when n different items are available and all of them are selected without replacement, the number of different permutations, or order counts, is npr, that's n factorial divided by n minus r factorial. For example, when testing a new drug, phase 1 requires only 5 volunteers, and the objective is to assess the drug safety. To be very cautious, we plan to treat the 5 subjects in sequence so that any particularly adverse effect can allow us to stop the treatments before any other subjects are treated. If 8 volunteers are available, how many different sequences of 5 subjects are possible? Alright, so because of this would be 8p5, so 8 factorial divided by 8 minus 5 factorial, so 8 factorial divided by 3 factorial. You could toss this into a calculator and SAS, do the math out, but you'd get an answer of about 6,720 sequences. Since the order of this does indeed matter, since we want this to be in sequence. For the permutations rule for some items that are identical to others, we have n items are selected without replacement, but some of them are identical. The number of different permutations, or order counts, when n items are available and all n of them are selected without replacement. But some of the items, though, are identical to others, and we can find this by n factorial divided by n sub 1 factorial times n sub 2 factorial, all the way up to n sub k factorial. Well, if we add up all those n sub 1 up to n sub k, we get the total n. And n sub 1 are alike, n sub 2 are alike, and all the way up to n sub k are alike. So, for example, when designing surveys, pollsters sometimes repeat a question to see if a subject is thoughtlessly providing answers. Just to finish quickly, for one particular survey with 10 questions, 2 of the questions are identical to the other, and 3 other questions are also identical to each other. For this survey, how many different arrangements are possible? Is it practical to survey enough subjects so that every different possible arrangement is used? So here we have 10 factorial divided by 2 factorial times 3 factorial. We toss this into a calculator, we get an answer of 302,400 possible arrangements. Now you might be wondering, if you add 2 and 3, you get 5, not 10. What happened to the remaining 5 that you need for this to make mathematical sense? That's because the only repeats that we have are the 2 and the 3. The rest of them are all 1s. So we have these. We also have 5 1 factorials in here as well. I didn't include them because, well, 1 factorial is just 1. So that's 3, 4, and then 5. Okay. So technically speaking, our calculations, this 10 factorial divided by 1 factorial times 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 2 factorial times 3 factorial. But again, all these 1 factorials are just 1, which is why they're technically speaking not needed to be written out exactly. But since there's 302,400 possible arrangements, it's usually not practical. It's not practical at all, because you don't need all of these arrangements. You usually only survey up usually about 1,000 people, depending on what you're trying to find. So you could cut down on this number of arrangements. For combinations, we have n different items available for selection. Only all of them are selected without replacement. And order does not matter. When n different items are available, but only all of them are selected without replacement, the number of different combinations, order does not matter, is found by NCR. That's n factorial divided by n minus r factorial times r factorial. So, for example, when testing a new drug on humans, a clinical test is normally done in 3 phases. Phase 1 is conducted with a relatively small number of healthy volunteers. Assume that we want to treat 20 healthy humans with a new drug and have 30 suitable volunteers available. If 20 subjects are calculated from the 30 that are available, and the 20 selected subjects all are treated at the same time, how many different treatment groups are possible? So 30 choose 20. This is the same as 30 factorial divided by 30 minus 20 factorial times 20 factorial. This is equal to 30,045,015 possible groups. And actually, before we do this example, I want to say one more thing about this this notation for n choose r being this lovely equation. We could also write this in a slightly nicer format as this, with n and r kind of what looks to be almost written such as a vector or a 1 by 2 by 1 matrix. But writing it in this form, n and r like this in the parentheses, this also means n choose r. But again, it's just another notation for it. But for example number 6 here, let's say the Portland Medical Center must appoint 3 corporate officers: Chief Executive Officer, the CEO, Executive Chairperson, and Chief Operating Officer, COO. And must also appoint a planning committee with 3 different members. There are 8 qualified candidates, and officers can also serve on the planning committee. I know how many different ways can the officers be appointed. Order here matters, right? We have 3 different possible choices: Chief Executive Officer, Executive Chairperson, and Chief Operating Officer. We don't want someone selected for one of these other roles to have gone to 2 roles at once. That wouldn't be good or fair for that matter. It's 8p3. 8 factorial divided by 8 minus 3 factorial. Toss that into a calculator, you get 336. For how many different ways can the committee be appointed? Well, order does not matter, so it doesn't matter who is selected at what time. They're all the same committee structure. That'll be 8 choose 3. So 8 factorial divided by 8 minus 3 factorial times 3 factorial. Toss that into a calculator and you get an answer of 56. For a shipment of 120 fasteners that contained 4 defective fasteners was sent to a manufacturing plant. The plant's quality control manager randomly selects and inspects 5 of these fasteners. What is the probability that exactly 1 of the inspected fasteners is defective? So we want the probability of 1 being defective. So from this, we need to slightly rework the way that we have these probabilities, right? Since most of the probabilities in this section dealt with nice and easy looking formulas. This one not so much. In the numerator of this, right, we need to have 1 defective fastener and 4 non-defective fasteners. Alright. And how do we choose the 4 non-defective fasteners? Well, if there's 120 total fasteners, so 120 total, we were told that there's 4 defective. Subtracting these 2 will give us a total of 116 non-defective fasteners. And since we have a total of 116 non-defective, from those 116 non-defective fasteners, we want to choose 4 of them. And likewise, to choose the 1 defective, there were 4 total defective fasteners. We want to choose 1. So 116 choose 4 times 4 choose 1. Divided by, for the total number of fasteners, right? For the total number of fasteners, we want to choose 5 total fasteners. Well, we have 120 total fasteners. We want to choose 5. So 120, choose 5. Alright. And then the calculation for this, once we toss this into a calculator, we would then get our answer for that. Just bear with me for 1 second as I go through that part of it. But we have that 116, and we want to choose 4 of them, times we have the 4 defective fasteners, and we want to just choose one of those, and we are dividing that by the 120 fasteners that we have. That total of 120 fasteners, and we want to choose a total of 5 fasteners from that. But when we toss that into a calculator, you would get an answer of about 0.1503. So about 0.1503 would be the probability of exactly one inspected fastener is defective. Thank you.